Welcome back to lab. So in lecture this week, we talked about correlational methods and correlations, regressions, multivariate analyses, that kind of thing. So in lab, we're going to also be doing correlations today. So what we're going to talk about is statistics review of descriptive analyses we talked a little bit about last week, as well as reminding about correlations and how to run correlations in SPSS, as well as generating the scatter plots that you need in order to display the data for a correlational analysis, along with that regression line or the best fit line that we talked about in lecture. So as a review for descriptive analyses in SPSS, it is always important that you are looking at your data before you run any analysis. This is the first step that a lot of people get too casual and they skip over. You're going to be looking for things like skew and the general central tendency of each of your measures. You want to check that distribution shape. You want to check to make sure the data kind of hang together. There's no weird data that's really going to mess up your analysis. You should always be aware of those outliers, which are these deviant scores that don't maybe belong in the data set. Now, it's always possible that they do, that you just have some unique individual, but you need to decide, and first to decide, you have to be able to look at those. You can do this by looking at the min and max of each scale, look at the range to see if it looks appropriate. And you can also graph the images, graph the scatter plot for your data if you're doing a correlational analysis. And this is how you can find online outliers as well as offline. A reminder from lecture that the online outliers are anything that is in the same pattern as the data that's on that best fit line, but is so far out that it's going to artificially inflate any correlational coefficient that you are calculating. The offline outlier, however, is something that doesn't match the data, it doesn't match the general trend of the data, and that's going to deflate or lower the correlation coefficient. So if you ever get a correlation that's really low and you think it should have been higher based on your hypotheses, go ahead and check to see if you have any offline outliers. Whereas if you have something that's an extremely high correlation that you're really kind of surprised to have found something that strong, go ahead and check to make sure you don't have any online outliers that might be pulling up that correlation. We have so far talked about how to write an introduction and a methods section, and the next section in your paper is going to be a results section. We're going to talk more in depth about the results in a few weeks and how to make sure all of the data you want is presented in those results. But just as a general preview, this section includes a summary of all of the data that you collected. It also makes sure to detail each of the statistical tests that you are using, such as an independent samples t-test that's comparing male and female groups on anxiety. You're always comparing two groups there. Or you could do a correlation to examine the relationship between two variables, such as anxiety and self-esteem. And then you want to give the actual results of that analysis. As a reminder, implications of what those results mean in the broader picture, the reference of what those results mean to inform your theory, that is not discussed in the results section. That's held off until the discussion section. You discuss the implications in the discussion. The results is simply where you're presenting the data, the actual findings without interpretation. You do need to have context. People need to see, you need to have the interpretation of the data of, oh, these variables are related, or one group had a higher score than the other, but that's where you stop. It is very objective information, whereas the discussion is more of the subjective and theoretical. Your statistical analyses for your results section are going to be these correlations or t-tests, and everyone is going to have either a correlation or a t-test in their paper. Again, there is a fringe group of you who might be interested in doing an ANOVA. I have not heard from anybody specifically. Maybe you're talking to your TAs, but make sure you reach out to your TAs or me well in advance if you do plan on doing an ANOVA, because we're not going to cover that in our lectures and our labs. So a correlation, that's always between two continuous variables. You should have heard that from me a million times by now. It shouldn't be a question. And we talked a lot in lecture this week about it displaying the relationship between two variables, this bivariate analysis, and then including the variance explained, which is represented by that r squared. This statistic should include a direction and magnitude if it is significant, and should be displayed with a scatter plot and a regression line. We're going to talk a lot about that today. The other option is the t-test between a continuous dependent variable or outcome variable and the categorical independent variable, which has two groups. If you have more than two groups, you need to reach out to me. You then compare the means of each group to tell if the differences between those groups in average score are statistically different, and you display this with a bar graph. That's the stuff we're going to talk about next week. So without further ado, let's talk about correlations. So a correlation is between these two continuous variables, and they are always going to be quantitative variables. There's numbers involved. We usually represent these variables as x and y. That's really appropriate for when we're doing our scatter plots. The x variable is on the x-axis and the y variable is on the y-axis. Now these two continuous variables can be switched up in any order. When you're doing a correlation, it doesn't matter which one is x and which one is y. They are bivariate. The relationship's going to be the same either way that you go. The basics of the correlation were discussed in the lecture video, as well as some things to watch out for. But as a reminder, a correlation ranges from a -1 to a +1, and it is denoted with the letter R for a Pearson correlation specifically. The scatter plot then that you build with all of the different individual combinations of score from every individual, that is going to be presented as a scatter plot with the relationship between x and y and that line of best fit that goes through them. As a reminder, correlation is not causation. There, I've got out of the way, I've said the thing. Only the two variables are related. It doesn't have any other information. You need to adjust for the temporal issues. You need to account for the third variables if you are going to try to make any kind of argument for a potential causation. But at the end of the day, no correlational method can ever answer problems of causation. There are three pieces of information that you will collect from every correlation analysis you do. Those are going to be the strength, direction, and the percentage of variance accounted for, that coefficient of determination. The strength, again, is from -1 to 1, which is a perfect correlation. Those are at the end, versus a 0 at the center, which is no correlation. And the closer a score is to 0, either from the negative end or the positive end, that means the relationship is weaker. There is less of that relationship. A 0 is no relationship at all. The direction is also important, whether it's a positive correlation or a negative. Talked in the lecture about a positive correlation is when you have both things working together. As one rises, the other score rises as well. As one participant's scores get lower, the other gets lower as well. A negative, though, is the inverse, whereas one variable scores increase, the participants show that their scores are decreasing, the bivariate relationship. The percentage of variance accounted for is that coefficient of determination that's telling you a more ratio scale of the effect size so that you can see how strong of an effect is this relationship having in the real world. How much of the outcome of one variable is explained by another variable? How much is there just chaos happening versus how much is just this other variable related? And you can calculate this with the simple process of squaring your R value, squaring that Pearson R. We also have the scatter plot, which is how we're going to draw. So you take every piece of data, you have its X and Y for each participant, and you simply map that out. So in our participants here, we have participant A, who has a 2 on the X-axis and a 9 on the Y-axis. So we'd go ahead and plot them, rising from the 2 and running from the 9. Then participant B has an 8 and 3. There we go. We have participant C has a 6 and 3. There we go. And then D has a 5 and a 5. So here we have 4 pieces of data that every participant has both scores on for their X variable and their Y variable. We can see just by eyeballing it that it looks like there's a downward negative path between these data points. And so we're going to draw a line of best fit there. That's going to be our regression line and shows that there is in fact a negative linear relationship between these data. Here's some other examples of the positive and negative correlations. These are the perfect 1.0 and -1.0 relationships. You can see that on a positive, perfect positive correlation, all of the dots are in a big row there. There's no deviation from that line. And the same thing is true for a negative 1.0, where there's no deviation from a line. It runs through every single data point without error. This never happens in real life unless you are correlating something with itself. You might get really high R values if you're doing an inter-item correlation, where you're expecting that people who answer one way on one item on your scale will answer very, very similarly to another item on your scale. Then you're going to maybe get closer to this 0.1 or negative 0.1, depending on how you designed your scale. Some other examples of a little bit less significant positive correlations, or less high effect size. So we have the R of 0.89 positive. You can see that there is a trajectory through this that is clearly a positive correlation, but there's a little bit more error there. It's still very close to that line, but there's some variance there. Whereas when you have a low positive correlation, yes, there is a general trend line through it, but there's a lot of error. There's a lot of difference of the mean, or squared difference from that regression line. So you can see the spread is increasing, the spread increases, which decreases the R effect size there down to a 0.39. And then here's an example again with the negative correlations, the same kind of thing. We have a negative trajectory that is going through the lines, through all of the data, but there's just a little bit of error is going to be a pretty strong negative 0.84 correlation versus the negative 0.4 correlation, which does go through the line. You can see that it is a negative relationship, but there's a lot of spread, so the effect size is weaker there. And then here's what no correlation looks like. You can glance at it and see there is absolutely no relationship. You can't really draw a good line, and if you did, there'd be so much error off of that line, so much variance from the line, that it would almost be meaningless. So there's no obvious pattern to these dots. You get an R of 0.00. As scores on one axis increase, there's no real relationship with the increase or decrease on the other axis. Speaking of strength and the magnitude, what is a strong or a weak relationship? Well, generally people use these R values to indicate strength. From a 0 to a 0.4, that's going to be a weak. Some people may call it very weak if it's closer to 0. We can generally get away with just the weak relationship. If it is from a 0.4 to a 0.6, it's generally a moderate. Again, there's a little bit of flexibility here. Some people will go all the way up to a 0.7 as moderate. And then anything above a 0.6, or again, maybe a 0.7 to 1 is strong. And you can see this represented in the scatter plots. You have that strong negative and strong positive. You have the weak positive, moderate negative, the weak negative, and none, of course, where you can't really draw any sort of line. So let's get some practice in interpreting these correlation coefficients. So you have a number of different R values here, and you need to include the strength and the direction. So go ahead and pause the video, and then when you're ready, you'll unpause, and I will go to the next slide. Okay, you've had a second to pause and think through it, so here are the answers. The first one, an R of 0.5, we would describe that as a moderate positive correlation because it is in the positive direction. As one score is increasing, the other score also generally increases, but it's in moderate because it's kind of right there smack between a 0 no relationship and a perfectly strong 1.0. Number 2, you have a negative 0.2. That is going to be a weak negative because you have the negative relationship there, but it's pretty close to 0 with the 0.2. A negative 0.9, however, is also a negative, but very strong. You can just say strong, but I might, in my research, even write very strong there because of how close it is to a 1.0. A 0.15 is a weak positive, whereas the 0.14 is starting to encroach on that moderate positive relationship. And then finally, you have that 0.05. This is very close to the 0, the midpoint, which is no relationship. That's going to be a weak correlation. So let's get some more practice running these correlations in SPSS and actually seeing this data. So for this activity, let's call it, you need to choose two continuous variables from that survey data s25_clean SPSS file. If you haven't already downloaded it, then make sure to now go and download it from Canvas, although you should have downloaded it by now. So just make sure you know where it is and how to find it. But it is on Canvas. If you are doing a correlation analysis in your final paper, I highly suggest that right now the two continuous variables you choose are the ones that you are going to use, so you can just get it done, get your analyses complete, and you're good to go. For my purposes and the demonstration today, I am going to be looking at college student stress, the college student stress scale, and the variable name is college stress average, and I'm going to be correlating it with self-esteem as indicated by the Rosenberg self-esteem scale and the variable name self-esteem_average. So that's the first and the third variable there. But again, you should be choosing anything that you like or choosing the ones that you are going to be doing in your analysis, which I guess are the ones that you like. To run a correlation in SPSS, you need to go into your SPSS file, make sure you go to Analyze, where we do all of our analyses, and we're going to be living here. We have been living here. Go down to Correlate, and then select Bivariate, because we are doing a two-variable correlation. Once that bivariate correlation window pops up, you're going to move over the two variables that you're interested in. Again, for me, it's going to be college stress and self-esteem. You then make sure that Pearson is checkmarked, that the correlation coefficient there. That will be the default, but if you've done anything in SPSS, choosing something else or clicking around, it might have changed. You can click the reset button at the bottom with the _R there, and it will reset to these settings of the Pearson tagged, as well as the flag significant correlations tagged. You want to make sure that's there to help you out as well. And then you go ahead and click OK. You don't need to do any of the options, any of the style or bootstrap. You have what you need. And once the OK is clicked, it's going to take you to your correlation output. Make sure you are going to your output window for this. Sometimes it pops up on a new screen or it pops up behind the scenes. Just go ahead and navigate to the output. And it should look something like this. Again, I am using college stress and self-esteem, but you could be using any two variables, any two continuous variables. So here we have the bivariate correlations and the pairwise data about them. And we don't need to look above the diagonal axis because the diagonal is always going to have a perfect one-to-one relationship with the variable because it is correlating the variable with itself. Remember, I said that a perfect correlation is always basically going to be something with itself. Well, here you get to see that evidence. But when we are correlating college stress with self-esteem, we get three pieces of data. The first is the correlation coefficient. Here it is a negative 0.514. We also get the significance, or the p-value, you might know it better as, and then the n, which is the number of participants who had scores on both variable. This is the sample size that was used for this specific analysis. Those are the three pieces of information you need. You're going to carry it with you. Make sure to note them down somewhere so that you can use them for your write-up later. When looking at the p-value, that's significance, we generally treat anything as non-significant if it is greater than or equal to 0.05. This signifies there is no relationship between the variables, that the true world has a relationship of 0, and anything that you got is just due to chance. It's not an actual relationship. Because whatever statistic you got is just due to chance, it is therefore inappropriate. It doesn't really make sense to interpret the magnitude and direction of that statistics because it's just random chance. It's not special because it didn't mean anything. So it's essentially equal to 0, so we don't talk about magnitude and direction at all. But if your p-value is significant, if it is less than 0.05, then you can interpret that there is a relationship between your variables. You interpret the magnitude and direction at that point because you are told it is not equal to 0 given its significance. When writing up and reporting your correlation, you're going to use all three of those pieces of information pulled from the correlation output table, as well as a last coefficient of determination, which you can calculate yourself by squaring your correlation coefficient. So when writing it, you put the R and then the parentheses with the sample size equals the correlation coefficient, comma, then a P equals, and you tell what the significance level is, and then you have another comma followed by R squared equals your coefficient of determination. So in our example here, a Pearson's correlation analysis was run to examine the association between college student stress and reported self-esteem. Stress had a moderate negative association with self-esteem. R of 93 participants equals a correlation coefficient of negative 0.51, which was moderate. Then the p-value was less than 0.001, that's the significance, and then R squared equals 0.26. I simply multiplied negative 0.51 by itself, and I got negative 0.26. Now, after you have figured out how to report your correlation, you should also think about how to visualize your correlation, which we know is done through a scatter plot. So how do you graph a scatter plot in SPSS? The first thing you're going to do is in SPSS, go under Graphs and go to Scatter Plot. So this is different from the Analysis tab when we're actually running the analysis, and instead now we're doing the visualization and the graphs. We're going to do the same graphing when we're doing t-tests so we can see that data. So any kind of visuals, you should think about this Graphs tab. You then go down to Scatter Dot and click it. It will pop open with a simple scatter, or with a scatter dot window. You are going to choose the simple scatter plot and then click Define. There are some other interesting forms of scatter dot that you can get, but this is the one that we're going to use. Then you get a window that is for that simple scatter plot, and you're going to move two continuous variables to the X and Y axis. I am again doing self-esteem and college stress, and I can choose either way I want it. I could have put self-esteem and college stress in the Y and X respectively, or I could have switched it up and put college stress in the Y-axis and self-esteem in the X-axis. Because it is a bivariate relationship, it does not matter the order at all. Then I click OK. Don't need any other options, just need those two variables. This will pop up in your output with a scatter plot. Ooh, pretty. Now I could glance at this and see if I see anything interesting. There is potentially one outlier there at the 1.0 and for college stress, and it looks like a 2.5 for self-esteem. So I might consider removing that, but I'm not going to do that just yet. Instead, I'm going to examine the relationship between my variables. I'm going to see what the line looks like, and then maybe I will rerun having removed that piece of data. If I want to get the regression line, I then have to double-click the graph. I double-click the picture, the scatter plot, and then on the pop-up window for a chart editor, I'm going to right-click and get Fit Line at Total. So again, I'm going to double-click the output window. It's going to have a pop-up window, and then I'm going to right-click on the scatter plot in the chart editor pop-up window and scroll down to Fit Line at Total. This will cause a wild regression line to suddenly appear in your data. Isn't that cool? You don't have to do any math. It's just there. So this is that line of best fit that goes through your image. And once you close down the chart editor, it'll reappear in your output. This line comes with the equation as well as the R squared, which is up in the top right-hand corner. In this example, with college stress used to maybe predict self-esteem with that regression, you have that self-esteem, the Y variable, equals 4.08 minus 0.36 times X, which is college stress. So if I knew somebody's college stress score, some new participant, and they had a 3.0 on college stress, then I could plug them into my equation with 4.08 minus 0.36 times 3, which is the same as 4.08 minus 1.08, which equals 3. So a college stress score of 3 should be predictive of a self-esteem score of 3. In fact, if you follow up from the 3 on your x-axis all the way up to that regression line, it's going to bump into the regression line right at the y-axis of 3.0, right where self-esteem is 3. So that's a good way to confirm that you're doing your math correctly. Once you have generated that graph in SPSS, you now need to put it into APA style, and this takes a few steps. First, you're going to remove the inner frame from your image. You then create the axis labels. So instead of just having college stress average, you might want to replace it with college stress scale. And the self-esteem, you could put Rosenberg self-esteem. You want to change the background to be white. You want to affect the font size for all of the Axis labels, the titles, the graph title itself. All of these should be consistent, and usually it's going to be the same text as the rest of the paper. So Times New Roman 12 point. You then can click to export it to Word, and you're going to add a figure caption to it. And we'll go over how those figure captions should be written and then numbered as appropriate later when we're going over all the details of APA style with graphs and figures. So here's some examples of the APA formatted graphs. The first one, you have time 1 is the X variable and time 2 is the Y variable. They've made sure to include that the range of potential scores for both time 1 and time 2 from 10 to 30. And then you have the regression line going through all of those data points. And at the bottom, you have figure X. They don't have a figure number in there. The relationship between scores on the Rosenberg self-esteem scale taken by 25 research method students on 2 occasions 1 week apart. Pearson's R of 0.96. So there we have given a lot of information about what we are seeing in this diagram. The figure title should always have a description so that the readers know what they're looking at. The second example, figure 7, there we have the temperature dependence on chirp frequency in central Maine. And again, we have the x-axis of chirps every 14 seconds. There's some information there that we can pick up. And then you have the temperature. The regression equation is up in the corner, the p-value, as well as the r squared. So there's a lot of information there. It's included a slightly increased amount of data, but it's still hitting all of the points that you need. And then finally, there's another example. This looks very similar, where the scatter plot showing the x and y axis, and it does include the regression line and the coefficient of determination there. All right, that's all we have for today. So just as a reminder, your introduction section is due on Monday. You should have gotten feedback for your literature review already, and you're going to be incorporating that literature review into your introduction section. So make sure to reach out to your TA if you're having any questions about that lit review, if you have any problems or unsure. And a reminder to focus on making smooth transitions between your paragraphs, making sure to include good logic that leads all the way from your opening paragraph through your literature review and into your hypotheses, and including that rationale. Make sure it is clear why you have come to the conclusion you have based on what you have written about. And then always be looking to APA style. I imagine a lot of you did pretty well, and then there were some comments here or there about how to make sure you're doing those in-text citations correctly. Next week in lab, we're going to talk a little bit more about results section write-up, do a little bit of review, and then begin transitioning to move on to talking about t-tests. And then, while you're worried about lab, also remember to focus on your lecture, because the week after this is exam 2. You'll have a week to do it. It'll be the same format of 2 hours and 100 points. So make sure to prepare for it. You all did pretty well on the first exam, so hopefully we can keep that up in this course. All right, that's it. Have a great week.